Algebra 2, Lesson 89, Conjunctions, Disjunctions, Products of Chords, and Secants. So we'll do a quick overview of this, and then we're just going to go straight to the practice problems. But conjunctions and disjunctions are graphing inequalities that are either connected, i.e. conjunctions, 2 points that are connected in the middle, or disjunctions, which are 2 points that go in opposite directions. Now sometimes before we graph these, we're going to have to solve some equations, or some inequality equations like these right here. And we'll go over that in a second. The other thing is products of chords and secants. And this is a big review of geometry as far as lines and how they relate to circles. So some really quick background information. A chord is any line that goes from one end of the circle to the other and passes and stays inside the circle. So these are chords, these lines. And then up here we have secants, and then we also have tangent lines as well. So this line right here is a secant because it begins outside of the circle, passes through the circle. And this line is a tangent because it starts outside the circle and it touches the circle at exactly 1 point. A tangent could keep going, but for the purposes of the problems we're going to be doing, all the tangents will stop at the circle, so that way you'll know they are tangent to the circle. And there's a couple equations that we just need to memorize for these two types of problems that we'll go over in a second. Now let's go to the practice problems. So, conjunctions and disjunctions. So on a number line, we need to graph the following disjunction. We have negative x minus 4 is less than and equal to negative 1. And then we also need to graph x minus 1 is less than 1, and then our domain is integers. So we're not going to be drawing straight lines, we're going to be drawing dots. Now before we can start graphing these, we need to solve both of them. And then one of the first things is we want to move this 4 to the other side for this inequality. So we'll add 4 to each side. We get negative x is less than and equal to positive 3. But the problem is we don't want to graph negative x, we want to graph x. So we'll divide each side by negative 1. And what happens is whenever you take an inequality and you multiply or divide by a negative number, you have to reverse the sign. So this changes to x is greater than or equal to negative 3. All right? So every time you multiply or divide by a negative number, reverse the sign. Now let's go to this one. Add 1 to each side, and then we get x is less than 2. So that one's easy. Now let's draw our number line. We've got 0. I'm going to start at negative 3. And I see that x is greater than and equal to negative 3. So I'll put a dot at negative 3. And then I can put dots at negative 2, negative 1, and keep going. But before I do that, I want to graph x is less than 2. So I'm going to go to 2. X is not equal to 2, so I'd put an open dot, but since I'm only graphing integers, I don't need to put any dot at 2. And then to show less than 2, I'm just going to go to the next integer, which is 1, and then draw that line. All right. So we see here, this is the graph of our solution. Our first spot being negative, and if you want to, you can put an open circle at 2. That's fine. I won't mark you down for that, but unnecessary. So we're starting at 2 and ending at negative 3, and this is our conjunction right here. The next example should be a disjunction, since the first one was a conjunction. We have negative 1 is less than x minus 1, which is less than and equal to 3, and this time our domain is reals. So first we have to solve this again. Now this one, since it's a conjunction, we see that x is involved in 2 different inequalities. So when I add 1 to x, I have to add 1 to each side of the inequality. So I add 1 here and I add 1 here. These cancel. This becomes 0. So we have 0 is less than x, which is less than and equal to 4. So I'll go ahead and draw my number line. I'll start at 0. I'm going to put an open dot since it's not equal to. X is greater than 0, so it's going to start going in this direction. Then I'm going to draw 4. X is equal to 4, so I'll put a closed dot at 4. And it's less than 4. So they connect right there. All right, well, I guess we didn't get a disjunction in this one, but that's how you solve those. Now let's go to chords and secants. So for our chord problem, we have a circle, which is not very well drawn. That's why I was using the circles in the books, because my circle is not so great. And then we have one chord here, and we have another chord here. This segment is x, here is 3, this length is 4, and the last segment is 7. Now, the equation we need to know for chords is pretty simple. All we need to know is that the lengths of the chord, when multiplied, will equal the lengths of the other chord. So in this case, 4 times 3 is going to equal x times 7. So we just set up an equation. It says 4 times 3 is equal to x times 7. Another way we could write this is if we simplify it. 4 times 3 would be 12, so we'd have 12 equals 7x. Divide by 7. X is equal to 12 over 7. Now, not all of the examples will be this easy. Sometimes your unknowns will be, like x plus 7. So then you'd have to, adjust your equation accordingly. But that's the gist of it. The segments of the chord, when multiplied, will equal the segments of the other chord that they intersect. Now, when it comes to secants and tangents, I actually have to do 2 examples here. We'll do the first one right here, and the second one will be down here. So we'll have this one, and then we'll have that one will be a tangent, and this one will have 2 secants. So if I have 2 secants, and this segment is 4, and this segment is x, this one will be 3 and 5. The rule here is that the outside segment will times the entire length of the secant will equal the outside segment times the entire length of the secant. So what that equation looks like is this. Since the outside segment here is 4, we're going to take 4 times the entire length of the segment, which is 4 plus x. Now that is going to equal the outside segment, 3, times the entire length of the segment, which is 3 plus 5. This is simply 8, and here we would use distributive property. So to rewrite this equation, we would end up getting 16 plus 4x is equal to 3 times 8, which is 24. We finish solving by subtracting 16 from each side. And then we get 4x equals 8 divided by 4, and we find out that x is equal to 2. That's 2. Now let's go down to this bottom example. We have a secant and a tangent. Now it's the exact same rule that we use up top, but sometimes this rule can get confusing for people when we use a tangent. So we'll take the same top segments. We'll say that this is 4 and this is x, and this bottom segment we will make 8. All right, so it's the same equation, which is going to be the outside segment times the entire length of the segment. The top is the same, 4 times 4 plus x, and that's going to equal 8, which is the outside segment, times the entire length of the segment, which also happens to be 8. So same rule, but it gets confusing for some people when you see a tangent, because they only see an outside segment. Even if the outside segment is the only segment you have, then you can still use that for the entire length. So here we'll distribute again. We end up getting 16 plus 4x equals 64. Subtract 16 from each side. 64 minus 16 is, I'm having a tough one on this. Let's see here, 48. It is 48. We have 4x equals 48. Divide each side by 4, and then we get x is equal to 12. So in this case, x is 12. That's it for this lesson. If you have any questions, let me know on Moodle, and I will see you in class.